Hello and welcome to the Curio Clips channel. Water covers more than 70% of Earth's surface, which means that a large part of our planet is always wet. But until about 4 billion years ago, Earth was dry as a bone, at least according to the evidence we have. So what happened next? According to some of the first scientists to really study the question, it was an event so huge that it fundamentally changed our planet forever. Water crashed into Earth. It didn't just rain either. It poured. We're talking biblical floods and maybe even bigger. The amount of water that fell on Earth back then is difficult to measure. But according to our calculations, it would be enough to cover our entire planet in a layer almost 600 meters deep. But wait a minute. If water wasn't around before this mysterious deluge, where did it come from? Today we don't know exactly what triggered the Great Flood, but we do know that much of Earth's water probably arrived here piggybacking on giant rocks from outer space. Asteroids and comets hurtling through the solar system are thought to have delivered most of the water we use today. They were icy projectiles full of frozen compounds that when they hit Earth's hot surface simply melted. As these chunks of space rock rained down on Earth, our planet started to fill up with water. Some scientists think that these impacts also brought organic molecules that jump-started life on Earth. Others believe that water was a prerequisite for life to emerge. Either way, without this cosmic delivery, Earth wouldn't be habitable today. So let's listen to the quiet gravity of water tonight. Let us trace its path across our planet's surface because it turns out that after this initial deluge, water reshaped Earth. It carved valleys and carved coastlines. It wore down mountains and created some of the world's most iconic landmarks. Water is a powerful force, but it works quietly and patiently, shaping the world in ways that we can only see over very long stretches of time. So in this episode, we'll try to hear the music in its motion. We'll listen to the rhythm of falling rain, the song of crashing waves, the whisper of melting ice, all of which have helped make Earth the planet we call home. We humans tend to think of water as a thing shaped by the land. Rivers run through valleys between hills and around rocks. Lakes collect in low spots. Oceans fill in basins. But before there were valleys, rivers, lakes, and oceans, there was just rock. In fact, at the beginning, Earth's surface was a jumble of newly formed solid rock. There were no valleys or basins yet, so water had nowhere to go. No wonder the first scientists who studied the subject assumed that giant floods were required to carve out these features. But today we realize that water didn't just fill existing holes. It actually created them. Take the Grand Canyon, for example. Today, the Colorado River runs through the heart of it, carving new layers of rock every year. But the river isn't responsible for the canyon itself. Instead, it's carved out a path through a pre-existing crack in the earth. That crack formed millions of years ago when two tectonic plates collided and pushed up the Rocky Mountains. Then water seeped into the cracks in the rocks. As the water flowed through, it picked up bits of rock and minerals. Then when it reached the base of the crack, it deposited them there. Over time, this process widened the crack. More water flowed in, and the crack got bigger still. Eventually, the whole thing collapsed, and the Colorado River rushed into the newly formed canyon. So while running through the canyon, the river didn't create it. Instead, it filled it in. Of course, this kind of erosion doesn't happen overnight, not even over the course of a human life. But if you step back far enough, you can see that water is incredibly good at moving rock and sediment. Seawater, for example, is slightly acidic. When it comes into contact with rock, it reacts with the minerals, breaking them down and carrying them away. On exposed coastlines, wave action can wear down cliffs by as much as a meter a year. Even if that doesn't sound like much, over thousands or hundreds of thousands of years, it adds up. Eventually, the cliff collapses and the cycle starts again. Each time a wave crashes into the shore, it carries a little more rock and sediment away from the coast. Today, we can see some of this material on beaches all around the world. Waves carry bits of rock and mineral from the seafloor, deposit them on the beach, and sometimes even further inland, creating new landforms and covering old ones. Beaches are constantly reshaped by wind and water, but they're also shaped by the kinds of rocks that make up the coastline. For example, if the seafloor is made of softer rock like shale, more sediment makes it to the beach. The result is a wide, sandy beach. But if the seafloor is made of harder igneous rock, waves can't erode it as easily. So less sediment reaches the beach, resulting in steeper cliffs instead. The same thing happens when ocean water laps against riverbanks, except here, the material moves downstream, eventually making its way to the ocean itself. River water can also carry nutrients that fertilize wetlands and deltas, which are the flat, low-lying areas of land at the mouth of a river where it empties into a lake or ocean. Fertile lands like these are some of the most hospitable places to live on Earth. Our own species and many others have built civilizations along river deltas for as long as we've been around. But while deltas can support lots of life, they're also highly vulnerable to rising sea levels. As the ocean rises, waves and tides can push further and further inland, flooding low-lying areas and washing away the soil that plants need to grow. Already, scientists have documented rising seas eroding coastal habitats and drowning islands. And the problem will only get worse as the climate continues to change. But as bad as that sounds, rising seas aren't anything new. In fact, they played a key role in shaping Earth's surface. About 18,000 years ago, during the last ice age, much of Earth's water was locked up in glaciers. Sea levels were about 120 meters lower than they are today. This exposed a lot of underwater land, including a land bridge between Siberia and Alaska called Beringia. Beringia was a huge region that allowed people, plants, and animals to move between Asia and North America. But as the climate warmed, the glaciers melted and sea levels rose. Beringia was the first place to go underwater, allowing the Pacific and Arctic Oceans to mix. That mixing created currents that carried warm water north, helping to moderate the Arctic's climate. But it wasn't just Beringia that disappeared. Rising seas also drowned river valleys, creating some of the world's largest estuaries. One of the biggest is the Sundarban, which drains a large part of India and Bangladesh. As the sea level rose, the Ganges, Brahmaputra, and Meghna rivers emptied their water into a giant, shallow pool. Today, the Sundarbans is one of the world's most biodiverse places. Its salty waters support unique plants and animals like the Bengal tiger and the bottlenose dolphin. Even in places where the land didn't sink, rising sea levels can lead to more erosion. Take the Florida Peninsula. For millions of years, the Atlantic Ocean has eroded Florida's east coast, creating a unique landscape of jagged cliffs and arches. But over the next 100 years, researchers predict that rising sea levels will double the rate of erosion, changing the landscape forever. Of course, not all changes caused by rising seas are bad. Around the world, rising seas have led to more sediment being deposited on beaches, leading to wider, more sandy shores. On some islands, the extra sediment has even created new land. For example, the island of New Ireland in Papua New Guinea didn't exist 200 years ago, but it emerged from the ocean as sediment piled up on top of a seamount. A seamount is an underwater mountain that was once a volcano. In other parts of the world, deeper water is becoming shallower. That might sound strange, but it's happening as water temperature drops and becomes saltier. When ocean water cools, it becomes denser and sinks. Water that sinks in the Arctic tends to stay there, which means less sediment builds up on the seafloor. That, in turn, leads to more sediment being carried to the surface and deposited elsewhere. Scientists don't know exactly how much sediment is being moved this way, but they do know that the seafloor in some areas is building up faster than it is breaking down. That's why tonight we're looking at water not just as something shaped by land, but as a force that shaped land itself. After all, Earth's surface is mostly underwater, and water's influence on that surface is everywhere. Rivers carve paths through the rocks. Oceans carry sediment to the shore. Waves crash against the cliffs, and tides flood coastal plains. Glaciers scrape and polish mountaintops. Water literally shapes the land underneath our feet. And it does all of that quietly. From plucking pebbles to polishing stones, water wears away at the rock around it. Pebbles are plucked from riverbeds and smoothed by tumbling. Rocks are polished by grinding against each other. Sand is ground from larger rocks and minerals. And all the while, water dissolves small amounts of rock and carries it away, making caves and shaping entire landscapes. Tonight, we're reminded of water's quiet power. It takes ages to create big changes, but over billions of years, it's reshaped Earth time and time again. If you find yourself enjoying the outdoors, take a moment to appreciate the slow, steady work of water. If you're near a river or lake, imagine all the rocks and sediment it's moved over the course of its lifetime. And if you're at the ocean, remember that the water you looking at right now might have been part of a giant prehistoric flood, a comet or asteroid impact, or even an ancient supercontinent. Thanks for coming on this journey with me tonight. It has been my joy to show you a tiny part of this amazing planet we all call home. See you next time.